Hello everyone. Today we are going to discuss semiconductor physics. And before directly going to discuss the semiconductor physics, we will have a quick review of the materials once again and how they are classified as conductor, semiconductor, as an insulator. And then we will start in detail the semiconductor physics, are particularly the semiconductors. So, uh, it is very important to acknowledge AI, particularly ChatGPT, is utilized for preparation of this presentation. As far as a reference is concerned, so this is the book Electronics Fundamentals, Circuits and Devices and Applications by Floyd, which has been also referred throughout this presentation. This is the outline which we are going to follow initially with the introduction to semiconductors, then diode characteristics, diode rectifiers, power supplies, and some special purpose diodes. As far as this first lecture is concerned, so in this lecture, we will focus on the introduction to semiconductors, some basic terminologies, and so on. So the first question is, what is a semiconductor? As we know, this semiconductor is a material whose electrical conductivity lies between that of a conductor and an insulator. So it means that conductor has higher conductivity, insulator has lower conductivity, while semiconductor has the conductivity in between them. Examples are, as we know, silicon and germanium, the group 4 elements, which has 4 valence electrons, are the 4 electrons in their outermost shell. And these materials are widely used in many of the electronic devices as well as different computer hardwares. So, to have a more clear look or the more clear position of a semiconductor, let's see this comparison. So conductor, its conductivity is very high. Example is copper, gold, silver, etc. Semiconductor, it has moderate conductivity. Examples are silicon, germanium. Insulator, very low conductivity. Examples glass, rubber, plastic, like that. So from this we get the idea of that where semiconductor lies. Now, why semiconductors are important? This is another question. And in order to realize this question, let's have a look on the different applications or the usage of semiconductor in different devices or in different components. So semiconductors form the basis of diodes. That will be our first major topic. Transistors, then integrated circuits, ICs, microprocessors, computer memory, and so on. So almost all modern technologies rely on this semiconductor technology. And this is why they are important. Now, within semiconductor, as we discussed, there are, although many other atoms, but among them, silicon and germanium are mostly discussed among the semiconductors. Although, again, between silicon and germanium, silicon is most widely used, and we will have the idea why silicon is more utilized than germanium. So in order to understand this phenomena, let's have a look on their atomic structure. On left side, we have silicon atom. On right side, we have a germanium atom. In silicon, there are total 3 shells, while the germanium has 4 number of shells. In silicon, the last shell is number 3, while in germanium, the last shell is number 4. Although they both have 4 electrons in their outermost shell, are 4 valence electrons, but because germanium valence electrons are at higher energy level than those in silicon, and therefore they require a small amount of additional energy to escape or to leave the parent atom. And this property makes germanium more unstable than silicon at high temperatures. Why? Because at higher temperatures, there are many chances of the thermal instability. It means that the electrons can leave their atoms at slightly higher temperatures. And we know in majority of the electronic devices, such as our mobile phone or other devices, there are the temperature rise. The heating phenomena are very common. So that's why silicon is more suitable, more stable in terms of the temperature. So silicon has more or higher thermal stability, and that's the reason it's most widely used semiconductor material. Now, when we are clear with this, let's start with the atomic bonding of the silicon. So silicon has 4 electrons in this outermost shell, or we can call it as valence electrons. These electrons form covalent bonds with neighboring atoms. And then we know in covalent bond, the electrons are shared. So each silicon atom shares electrons with 4 neighboring atoms. Let's see from this figure. So these are the representations of a silicon with 4 neighboring silicon atoms. And we have 2 looks, either in terms of the atomic structure or in terms of the bonding diagram. This is called bonding diagram. So this creates a stable crystal lattice. Now, as we are familiar with this atomic bonding, we can now understand the energy bands in solids in general, and then we will see what is the value of the energy gap for silicon. So, in semiconductors, electrons occupy energy bands. The 2 important bands are valence band. It means it contains valence electrons, and electrons are bound to atoms. So when electrons are within their atoms, until and unless they have not left their parent atom, it will be called valence band. Now, conduction band means electrons have left their parent atom and now they are free to move. And because they are free to move, so they are responsible for the electric current. And between these 2 bands, there are energy gap, which is called band gap or energy gap. So we can see from this figure. Now this is nucleus. First shell, our first band, 2 electrons. Second shell, our second band, having some electrons. Within each band, there is energy gap. Now this is because this is the last shell. So this is valence band. These are the electrons, and there is some energy gap. This energy is needed to electrons of the valence band to become free from the parent atom or to leave their parent atom and to come in the conduction band where they will be responsible for the electric current, or where they will be free electrons because they will leave their atom. So at this time, there is no electron in the conduction band. So this type of diagram is called energy diagram or energy band diagram. Now let's try to understand how these conduction electrons and holes are created. So initially, when an electron jumps to conduction band, a vacancy is left in the valence band within the crystal where it has left its empty space, and that vacancy is called hole, as we can see from this figure. So this is the valence band. 2 electrons from this valence band has been moved to conduction band with some external heat energy, and as they have moved to the conduction band, so their left space, their left vacant space is now treated as a hole, and they both, electron and hole, now they are treated as an electron hole pair. There is also a possible reverse phenomena when electron jumps return to the valence band from the conduction band. So now this is electron. If it loses its energy and fall back into its hole or the empty space, so this is called recombination. So from this we get the idea that how an electron and a hole pair is generated, and this free electron is basically responsible for conduction, and due to this reason these electrons are also called conduction electrons. Now if we summarize, this is a silicon crystal. In this silicon crystal there are many silicon atoms. In these atoms, electrons have left from many places, so they have resulted in generation of electron hole pair. When electron comes or falls back into a hole, so this is called recombination of electron with a hole, and this generation of electron hole pair is important to understand onwards that how actually the current flows in these materials. So before understanding the current flow, let's have a quick view on the band gap or energy gap. So the band gap is basically the energy difference between two bands, and these are the valence band and conduction band. Particularly for silicon, this energy is 1.1 electron volt. So this is the value of energy. Its unit is electron volt. And this small band gap allows electrons to move to the conduction band when this much energy is supplied. Now, as we already know, the charge carriers, so there are two types of charge carriers. One are the electrons. They have negative charge, and of course they will move in the conduction band. Other are holes. Actually, holes are the vacant space are the vacancy, are the absence of electrons, so they are treated as positive charge and they represent the absence of an electron, and both contribute to the current flow. So electrons as well as holes, they both are responsible for current flow. Keeping this thing in mind, let's try to understand the electron and hole current. That means current due to electrons, current due to holes. So from this diagram, this is a semiconductor material based on silicon, and it has been supplied with some voltage. So when it is supplied with some voltage, of course, that voltage would have some polarity. So plus is on this side, minus is on this side. We know electrons will be attracted to the positive side. So we can see the direction of these electrons which are being attracted to the positive side. Now we can see the electrons are moving from left to right direction. So we can say the holes are moving in the opposite direction, because as electrons will move from left to right, so they will fill the holes on the right side and will leave the holes on the left side. So we can say holes are moving from the right to left. The same thing we can see from this diagram in a more detailed view. We can see these electrons. These electrons are moving from left to right. So they are leaving the vacancy, a hole in the left direction. So we can say the holes are moving from right to left. Now, one thing which is very important to note over here is that actually there is the movement of only electrons, but because electrons move and leave their space, so they leave a hole on their backside or behind. So we treat holes also as a movement or as a charge carrier. So actually only electrons are moving, but we see both as a movement, electrons as well as holes opposite to each other. Now let's compare again the semiconductors to conductors and insulators, but now at this time in terms of the energy gap. Already we have seen this comparison in terms of the conductivity, but now we are seeing this comparison in terms of the energy gap. So on the right side, we have conductor in which valence band and conduction band are overlapped. It means at normal room temperature even, there are the availability of free electrons in the conductor which can participate to the flow of current. While on the very left side, we have insulator in which the energy gap between valence and conduction band is very high. That's the reason that free electrons are not easily available, and definitely there will be no flow of current. While in semiconductor, this band is slightly higher than the conductor and lower than the insulator. So with some energy, with some external energy, electrons can become free electrons and they can participate in the conduction. So this is how, on the basis of energy levels, these different materials are. Now, the when the semiconductor is in its pure state, it is called intrinsic semiconductor. Intrinsic means a pure semiconductor without any impurity. So examples are again pure silicon, pure germanium. Properties equal number of electrons and holes. Of course, they are in their pure state. And the drawback is that the conductivity is relatively low in their pure state. So in order to increase the conductivity, what we do, we add some impurity. So the process to add the impurity is called doping, and then the semiconductor is called extrinsic semiconductor. So when impurities are added, semiconductor becomes extrinsic, and this process of addition of impurities is called doping. In the result of doping, we get two type of materials now: n-type semiconductor, and when it is resulted, when there are extra number of electrons, we will see how electrons become extra or in excess. So this will result in n-type semiconductor. Other type is p-type semiconductor, when there is deficiency of electron, or we can say a hole, a vacancy, so extra holes are created. This will result in p-type semiconductor. We will again see how this is being created, and this concept will lead directly to PN junctions and diodes that we will discuss. So we are concluding this introduction over here. In coming lecture, we will continue with the doping, then how two types, N-type and P-type, are created, and then we will continue this discussion to the PN junctions and particularly diodes. Thank you so much. If you will have any query, so we will also discuss these queries in the live session. Take care. Bye.